Welcome to this lecture in EE557. In the last lecture, we have seen that the Markovian property is guaranteed for one-step transition PDFs if we assume independence among the basic random variables. But we have seen that in the case of m-step transition PDFs, the independence assumption is not sufficient for having the Markovian property. Remember, for a system to be Markov, the Markov property should hold for all m-step transition PDFs. Therefore, we have to investigate this case. In the last lecture, we have seen an example and talked about the reason for this problem. And in this lecture, we are going to see a more systematic way, or the general case of the reason of the problem. And then we are going to talk about the solution. There are two solutions, as I talked about in the last lecture. And the first solution is to make the feedback only a function of the current output. The second solution is to assume deterministic inputs after some point in the transition PDF. The book that we are trying to cover in this chapter takes the latter approach, and that is what we are going to do in this lecture. So let us talk about the system, the stochastic system. I have the state equation given like this, and the output equation is hk, xk, vk, and the state feedback is gk, y0k. Remember, last time I talked about the problematic thing about this feedback. We see that the feedback is dependent on, the input is dependent on the current and the previous outputs, and the dependence of the feedback on the previous outputs is causing this problem in the m-step transition PDFs. So here, this is my system definition. And here I would like to just look at the basic case. We have actually seen a specific system, and we have investigated these distributions on the example. So I have here a two-step transition PDF. So I have this U, 0, and I have 2 here. This is the first PDF. And we can say that in general, this is not equal to x3, and I have x1 and U12 here. Okay? In general, we don't have this equality. And this is just a two-step transition PDF. So we see that the Markovian property does not hold in general for this type of feedback structure. Remember, I told you that if the input is not selected in a feedback, and if the input is deterministic, then such a property would hold for any m-step transition PDF. But when the input is chosen in a feedback loop, while the feedback loop here, feedback rule here, is dependent on the previous outputs, then that is actually causing the non-Markovianness, is bringing non-Markovianness into the system. So now let us try to investigate this two-step transition PDF. So I can do this investigation by thinking about this transition distribution. So I have 0, 1, U0, 2 here, and I have x3. Okay? This is the distribution corresponding to this density, PDF, and I can write it as P. X3 is inside capital X3, an arbitrary subset inside the state space, and I have here x01 and u02 here. Okay, this is the first first distribution, and I can write a distribution for the second PDF here as well. So now I'm going to try to express x3 in a recursion in terms of the state here, x1, and the inputs u1 and u2. I will try to express the state x3 in terms of x1 and u12 here. Let us now try to do that. So I have probability. Instead of x3, I'm writing f2 here, x2, u2, and w2. This should be inside capital X3, x01, u02. Okay? And instead of x2, I can use this recursion once more. So I have p, f2. Now I write here f1, x1, u1, and w1. I close the parenthesis for f1, then I add u2 and w2. Close the parenthesis for f2, then this has to be inside x3. This is my event, and x01, u02, they are given to us. So in this investigation, I am going to call the quantities related to this distribution with one parenthesis, and I'm going to call the quantities related to this PDF with two parenthesized. So I have this is related to 1 here. Okay? Now you see here there are some given quantities here in this PDF. Oh, sorry, in this distribution. And you see that x1 is given, so it is given, and u1 is given, and u2 is given here. Okay? And as a result here, in this expression, these functions f1 and f2, they are known. And x1, u1, u2, they are deterministic because of the given conditions. And I have w1 and w2 as random variables on the left-hand side. Now I'm going to write the probability distribution for the second PDF. Okay, that is going to be given by 2 p x3 given x01. Sorry, in this case only x1 is going to be given. The past is going to be forgotten when the last state is given, and the past inputs would be forgotten when the last state and the last input are given. So I have u12 here. This is going to be x3, and this is going to be, I will make a similar calculation here, but it is going to be just the following. So I would have f2, and I have f1, x1, u1, w1, and u2, w2, close the parentheses, in x3 given x1 and u12. Okay. Now here I have the same thing. x1 is given, u1 is given, u2 is given. Okay. So here we see that both of these probabilities, these events that I'm trying to calculate the probability of, can be converted into events related to w1 and w2. Okay. This event for an arbitrary subset x3 is going to happen if w1 and w2 are in some subset which would depend on x1, u1, and u2. Okay? So here, instead of these expressions, I can write the following probabilities. Probability w12, the noisy terms, the other ones are deterministic, they should be inside a subset of the joint space of w1 and w2, which would depend on x1, u1, u2. In the earlier lecture, we have actually proven a lemma, and we have used a similar concept. This W1, capital W, 1, 2, is the set of W12s which would make this expression satisfied. Okay? I can define a subset, W12, is the set of W1s and W2s, which would actually make this expression, make this event happen. All right? Given I have here x01 and u02. I can do the same thing here for the second probability as well. P, W12, inside W12, x1, u1, u2, given x1, u12. Okay? So now I'm going to concentrate on the given informations for both of these probabilities. So we see that if the, so this is an, these are the, in both of the probabilities I have the same event. Okay? We see that these two events are related to the random variables W1 and W2. If the given conditions are not dependent on W1 and W2, if the given conditions do not give us any information about W1 and W2, then I can remove these conditions and both of the distributions would be the same. Both probabilities would be the same. But here we are going to see that these given conditions cannot be removed because here U2 is going to give us information about W1, and that is why these two conditions cannot be removed here from the conditionings in general. So let us look at the sources of information here on the right. The first condition is x0, and this condition is only in the first probability. Okay? It's one of the basic variables. Sorry. And the next piece of information is x1. Okay? And you see that x1 is given in both of the conditionings of these probabilities. Okay? It is in both 1 and 2. And we know that x1 is f0, x0, u0, and w0. Okay? And u0 here is g0 of y0, and g0 of y0 is h0, g0 of h0, x0, and v0. Okay? So we see that x1 is in general a function of x0, v0, and w0. And we know that these variables are independent with w1 and w2. Why? Because of the independence assumption. So under the independence assumption of the basic random variables, assumption A, we see that x1 is independent with w1 and w2. x0 is also independent with w1 and w2. As a result, these two quantities cannot give any information about this event here, because they are these random variables x1 and x0, they are both independent with the random variables w1 and w2, and that means that they don't provide any information in these conditionings about these events. Now let us go into the next piece of information. This is going to be u0. u0 is only in the first probability. Okay? And we know that u0 is g0, h0, x0, v0. I have already done this calculation here. So I have this expression. And you see that u0 really doesn't give us any information about w1 and w2 either. Okay? So this piece of information really does not give any info about w1 and w2 by itself. Let us look at the next piece of information. It is u1. u1 is in both of the probabilities. u1 is, we know that it is g1, and I have y01. And this is therefore g1. a function of both y0 and y1. h0, x0, v0, h1, x1, v1. And here, this x1 is nothing but f of 0, x0, u0, and I have w0. So you see that here, u1 also cannot give any information about w1 and w2. It is because, so this u0 is also this, g0, h0, x0, v0. And you see here that u1 is only dependent on the basic random variables x0, v0, v1, and I have w0. And all of these basic random variables are independent with w1 and w2. As a result, the information of u1 cannot give any information about this event either by itself. Okay? So far, all of the things that we have seen, all of the given conditions that we have seen, they do not provide any information about w1, 2. So if these were the only given conditions, I could have removed them from the given conditionings. And then these two probabilities would be the same. But we know that in general they are not the same, and we are looking for the reason. And these are not going to be the reasons. The reason is going to be the last piece of information, which is u2. So u2 is g2 y02. Okay? And we know that this u2 is g2, a function of both y0, y0, y1, and y2. And I have h0, x0, v0, h1, x1, v1. This is y0, y1. And I have h2, x2, v1. I have already investigated these pieces of information, and these are not a function of w1 and w2. On the other hand, this last piece of information, h2, it contains x2, and x2 is f1, x1, and I would have u1, and I would have w1. So you see that u2 is a function of w1 as well. Okay? So as a result, this u2, due to u2 here, I cannot remove these conditions, these information from the given conditions here. Okay? Because u2 is a function of w1. As a result, whenever u2 is in the given conditions, I cannot make removals of terms from the given conditions here. Okay? Because u2 is providing us information about w1, which this event is with respect to. Okay? We see that u2 is in both of the probabilities. Okay? So then why these probabilities are different? u2 is in both of the conditionings of these probabilities. Why are these probabilities different in general? Remember, these probabilities are different only because of these two terms. Okay? x0 and u0. They are the given information which is different than the given information for the second probability. Okay? So x0 and u0 are the extra information given in the first probability than the second probability here. So why does the existence of x0 and u0 make these two probabilities different than each other. So now let us concentrate on U2. So you see that U2 contains many random terms. X0, V0, X1, V1, and I have X1, U1, W1, V1, etc. Okay? In the second probability, X0 doesn't exist. In the second probability, in the given conditions, X0 doesn't exist. As a result, U2 provides information about W1 under the non-existence of X0. So X0 is just a random variable for the second probability. Okay? So I can actually write the following simple expression as an example. Let us say that this is X0 plus X2. Okay? So then, just as in the example that we solved in the last lecture, this is X0 plus F1, X1, U1, and W1. So you see here that U2 gives us information about W1, and here, if X0 is not known, as you see in as it is the case in the second probability, X0 here acts as a noise. Okay? When X0 is not known, as in the case in the second probability, X0 here, the initial state, just acts as a noise term in the measurement of W1. Okay? So this U2 then gives us some noisy information about W1 in the second probability. Okay? So I can think that I know what U2 is, and U2 is a kind of measurement of W1. Okay? And if X0 is not given to me in the given conditions, this X0 acts as a noise term for us in the second probability. And this means that the information of the measurement of U2 would give us some noisy information for W1. But in the first probability, X0 is known because X0 is given in the conditions. In that case, for the first probability, this term is known. As a result, W1 is then measured in a better way when U2 is given in the first probability. Okay? So we see here that for the second probability, X0 decreases the quality of information in U2 about W1. Okay? For the second probability, X0, the fact that X0 doesn't exist in the given conditions would decrease the quality of information in U2 about W1. But in the first probability, X0 is given to us. So it is like we are knowing this unknown term here in the first probability. As a result, we know W1 in a better way by knowing U2 in the first probability. Okay? So this is the reason why these two probabilities in general are different than each other. If in the input term, if I have the dependence of this input on the previous state variables, these extra information in the first probability would bring us advantage about knowing W1 here. Okay? So X0 and U0 knowing them will bring us more information about W1 when we know U2. Okay? As a result, these two probabilities would be different in general. So the quantity U2 will provide different amount of information about W1 when we know x0 and u0. Okay? Because of this type of reasoning. In the second probability, x0 decreases the quality of information in u2 about w1. On the other hand, in the first probability, we know x0. As a result, we know w1 in a better way in the first probability case. So here we see the reason for these probabilities being different. So how can I actually get rid of this reason here? One way to actually get rid of this problem, to avoid these probabilities being different, is to assume that U2 does not depend on the previous measurements. Okay? So I can remove this dependence, and I can remove this dependence. Then U2 in both probability, in both conditionings, would provide the same information about W1. In that case, if I can get rid of this dependence, if I make the input only a function of the current state, then I can, the U2 in both conditionings here would provide the same information about W1 in both of these probabilities. And in that case, I would have equality here. And in that case, I would have equality in these PDFs. That is the first way to avoid this problem. The second way is actually a kind of overkill. And the second way is to assume that this U2 really does not depend on any of the previous measurements. So the second way to get rid of this problem is to assume that U2 is not dependent on the outputs, meaning that U2 is selected in an open loop, okay? Meaning that U2 is selected deterministically, okay? If I choose U2 deterministically, then it won't depend on any of these quantities, and because the earlier quantities do not give any information about W1 and W2, I will be able to remove these conditionings from both of these probabilities in that case. And in that case, these probabilities would be equal as well. Okay? That is what the book suggests. The chapter that we are covering in the book would suggest. Okay? So let us try to assume this. Let us assume that U2 is deterministic. That means that U2 really does not depend on any of the previous states or the current states or the current outputs. So U2 is selected deterministically means that we choose U2 in an open loop. So suppose U2 is deterministic. That means that U2, which is equal to G2 Y0K, sorry, Y02 here, my note is also wrong, that is equal to U2 bar. U2 bar is a deterministic value here, okay? If we make this selection, then what happens? Then U2 will not provide us any information about W1 either. Okay? So this is not going to bring us any information, and the others are not bringing any information either by themselves. That means that we can actually remove these conditionings from these probabilities, and we would have the following. The first probability would turn into W12 inside W12 X1 U1 U2 with no given conditions, and 2 is probability the same event x1, u1, u2. And you see that these are nothing but the same probabilities. Okay? So we have equality. Okay? So now think about what would happen if we considered the following distribution. Px4, so I increase the m value. So this is a three-step transition probability. x0, let us say 1, and u0, 3 here. Then I can consider the equality of these. x4, x1, u1 to 3. So instead of x3, I put here x4. Okay? So this is a three-step probability equality. In that case, what would happen? The only change that would be is this W12 would be W123. Okay? So I would have W from 1 to 3. This would be W from 1 to 3. These would be x1, u1, u2, u3. x1, u1, u2, u3. And here I would have increased these 2's. So what is happening in this case would be these 2's would be turning into 3. Okay? And in that case, U2 would again be dependent on W1, and U3 would depend on both W1 and W2. Okay? So in that case, this type of dependence would be encountered in a more severe way here. Okay? In addition to U2, I would have U3, and U3 would depend on W1 and W2. And this information here would be, this random variable would be here, W1 to 3, and I would have dependence of U2 and U3, both on W1 and W2. Okay? In that case, in order to be able to have the same result, I need to assume that U2 is deterministic and U3 is deterministic. Okay? I need to assume that both inputs are actually deterministic for the four-step transition probability equalities here. So you see that when I increase the step of the transition PDF, I need to assume more inputs to be deterministic to have the Markovian property satisfied. So that means that when m increases, we have to assume the inputs uk plus 1, uk plus 2, going until uk plus m minus 1 to be deterministic. For the Markovian property to hold. For the Markov property to hold. Okay? So now we are actually ready to write our lemma about m-step transition probabilities. Lemma. under assumption A, that is the independence of basic random variables, we have pxk plus m given x0k, u0k, and I would have the deterministic input sequence uk plus 1 to uk plus m minus 1. That is equal to pxk plus m given xk, uk, and I have uk plus 1 to k plus m minus 1 bar, where uk plus 1 to k plus m minus 1 bar are deterministic inputs, meaning that they are open loop constant quantities inputs. Okay, but as I told you, this is kind of overkill, so we could have achieved a similar result if we assume that we had feedback inputs which are dependent on only the current output. Okay? So this actually completes this complicated concept of transition PDFs and Markov property. And in the rest of this lecture, we are going to see some properties by assuming that this type of property would hold. So let us write lemma. M-step transition PDFs can be obtained recursively as, so I'm going to write two lemmas here. This is the first one, and both of the lemmas are going to give some recursions for these transition PDFs. And I will assume here that this type of property would hold for the transition PDFs, but in order to be able to have some brevity, I won't write here U bars, okay? So in order to be able to assume that such property holds, you need to assume that these inputs are deterministic, but the book does the same here. So although we are assuming that these inputs are deterministic here, we are not going to write bars here, but we will instead just show it just with uk plus 1 to k plus m minus 1. And actually I'm going to combine these two terms, which is going to be u from 0 to k plus m minus 1. Okay? So let us write the recursion for the transition, m-step transition distribution here, transition PDF, is given as, I have an integral k plus m minus 1, and I have, sorry, I'm writing the wrong thing here. I need to write the first one. So I have this m-step transition PDF is given as xk plus m, xk plus 1, uk plus 1 to k plus m minus 1, and I have one-step transition PDF here, xk, uk, and I have the xk plus 1. So this is a form of recursion for the transition PDFs when this type of Markovian property would hold. Okay? In general, what we are doing is that I am writing this m-step transition PDF in terms of m minus first order transition, m minus one step transition PDF, and one step transition PDF here, as an integral of m minus one step transition PDF and one step transition PDF. So I will give the proof of this. It is not really difficult once your probability theory knowledge is sufficient. So here is how I can prove this. So I have xk plus 1, xk, uk, k plus m minus 1. So first I'm going to write this PDF as a marginal of a joint PDF. Okay? So I have, this is going to be px k plus m, and I'm going to add the additional variable xk plus 1 here. Given, xk would be still given, and uk to k plus m minus 1 is still given, and I have the integral with respect to xk plus 1. So you see that this integral is nothing but the marginalization of this joint conditional PDF and then obtaining the marginal conditional PDF here. Now I'm going to write this joint PDF as the multiplication of two distributions. And the first PDF is going to be this one. I will take xk plus 1 to the other side. xk, uk, k plus m minus 1. And I would have p, xk plus 1 given xk, uk to k plus m minus 1. Okay? dxk plus 1. So how did I write this last equality here? Let us try to understand that. This is nothing but the conditioning rule with extra conditionings. Let us try to understand that. In the probability review part, we have seen the following rule. If I have some events, this is nothing but this. And if I have some extra conditionings here, I can write this. BC, P, I can actually write here AB given C, and I will write here P, B given C. C is common to all probabilities here. And here, while writing this joint distribution, in terms of as the multiplication of these two distributions, I have used that type of equality here. So my A here, it is nothing but xk plus m, okay? And my common B is xk plus 1. I have some equivalence here. And the C is the common conditionings, xk, and I can actually write these like this, and xk and uk, k plus m minus 1. Okay. If you use this type of definitions, then you can write pxk plus m given conditioning here. I have xk plus 1, xk, I am writing B and C, uk to k plus m minus 1. That is equal to PAB given C. I have xk plus m, xk plus 1, given xk, uk, k plus m minus 1. So I have this joint distribution, joint conditional distribution, divided by PB given C. P, xk plus 1, given, I would have these conditionings. xk, u, k given, k plus m minus 1. Okay? So you see that then this joint conditional distribution is nothing but the multiplication of these two distributions. Okay? That is what I have done here. This joint distribution was written as the multiplication of two distributions here. One this one and this one. Okay? So here I'm going to assume this Markovian type property. So what you can do here is that assume that these inputs are deterministic. Okay? Let us assume that all of them are deterministic. All right? In that case here, when I look at this distribution, I know that I can here remove this xk due to Markovian property, because xk plus 1 is already given. I do not need any previous state. Similarly, instead of, I can actually remove uk from here as well. Okay? Because uk plus 1 is also given. Alright, so instead of this, I can write uk plus 1 to k plus m minus 1. Okay? So here I use this Markovian property by assuming that the inputs are, let us say, deterministic. I removed uk and xk. Okay? Because xk plus 1 and the inputs starting from k plus 1 to k plus m minus 1 were already given. So I removed xk altogether and I have removed uk from here. And when I look at here, I see that xk is given to me, but uk is also given, but there are also some future measurements. The future measurements, I'm assuming all of the inputs to be deterministic here. That means that the future inputs, sorry, not measurements. So I have some future inputs here, and these future inputs, I am assuming them that they are actually deterministic. So these future inputs cannot give us any information about xk plus 1. I am assuming that they are deterministic. So now instead of this, I can just write here uk. I can remove all of the future inputs from the conditioning. Because when the future measurements are deterministic, then they cannot give us any information about xk plus 1. So the only terms in the conditionings that can give information about the xk plus 1 would be xk and uk. Future measurements do not provide us any information about xk plus 1 when they are deterministic. That means that I can continue here. I can replace my integral by the new conditionings here. P x k plus m given xk plus 1 uk plus 1 to k plus m minus 1 here. And I have pxk plus 1 given xk uk, and I have the xk plus 1. But this is nothing but the statement of the lemma. Here we need to assume the deterministic inputs here. Okay? Without the deterministic inputs, this type of removing these future, I can, for example, if the inputs were not deterministic, I could not have removed these future measurements from the conditioning here in the second distribution. Because then the future measurements would be a function of the state xk plus 1, and then I wouldn't be able to remove them from the conditionings. Okay? So this was the first lemma, which gave us a recursion about the m-step transition PDF. And now I will write the second one. This second one is not in the book, but you can derive it very similarly. It's the same statement. M-step transition PDF or PDFs can be obtained recursively as P xk plus m given xk uk from k to k plus m minus 1. And I would have the following integral. P xk plus m given xk plus m minus 1 here. And I have uk plus m minus 1. Close the parentheses. And I have P of xk plus m minus 1 given xk uk from k to k plus m minus 2. And I need to take the integral with respect to xk plus m minus 1. So this is the second lemma. I'm not going to prove this in the class, but I have written the proof already into the notes. So you have to make sure that you can actually derive this yourself by assuming that the inputs are deterministic. Okay? So that completes the recursive nature of these transition PDFs. And the last topic that we're going to see in this lecture is going to be the alternative description of Markovian stochastic systems. This is the last section in the chapter that we are trying to cover. Actually, as you see, this chapter was quite conceptual and difficult to understand, especially these transition PDF parts. When we start with the new chapter, you're going to see that things are going to get less conceptual, and you're going to be able to visualize the concepts in a better way. So let us write alternative description of stochastic Markovian systems. Let me first write the standard description. We have already seen it. The standard description is the state equation, and process noise is a white sequence, and I have the distribution of the process noise. Okay? That is my standard description for the state equation with the process noise. And I have the measurement equation, yk, hk, xk, vk, and of course I need to provide the distribution of the measurement noise, vk. Okay? What else do I need to provide? I need to provide a description of the initial state by providing its distribution. And I need to provide the input rule. Okay? uk, gk, y0k. All right? So now let us look at the alternatives here. So the alternative description for the state equation and the distribution of the process noise is the following. We only provide the one-step transition PDF. Okay? So I can actually summarize this function. So as you see, if xk and uk is given to me, then xk plus 1 is a function of the random variable wk. Okay? So if xk and uk are given to me, and if the distribution of wk is given to me, then I can calculate the one-step transition PDF. xk plus 1 given xk and uk. So this single one-step transition PDF summarizes both of this information at the same time. Okay? So this is one-step transition PDF. The situation for the measurement equation is similar. So both of this information can be summarized by giving the conditional distribution of yk given the state xk. Okay? Because when xk is given, the distribution of yk can be calculated from the distribution of vk only, this distribution. So this conditional distribution summarizes both of these pieces of information at the same time. And this piece of information, this conditional distribution, is called the likelihood. Okay? That is the likelihood function of the output. And these two are the same. They do not change. Px0, x0, uk. So I can give you here a very simple example, which we are going to investigate in the next lecture. For example, I can have the linear system xk plus 1, axk plus buk plus gwk. And suppose that wk is normal with 0 mean and covariance q. In this case, we are going to see that these two pieces of information can be summarized in the conditional distribution. Xk plus 1, xk uk is going to be normal xk plus 1, and the mean is going to be axk plus buk, and the covariance is going to be gq, G transpose. So I would either give these two pieces of information, or I just give that transition distribution. I have not talked about why that transition distribution is given like that. We're going to derive it in the next lecture, when we go into the new chapter called Properties of Stochastic Linear Systems. So we will talk about how this distribution was obtained in this manner. The output equation for the linear system is going to be Cxk plus HVK, and Vk is going to be normal with 0 mean and covariance R. In that case, I will summarize this distribution, these two pieces of information, with the conditional distribution of yk given xk, which is the likelihood here. And that is going to be normal yk cxk, and I would have hr, H transpose, as the covariance. Finally, the common distribution here in both of the cases would be x0 normal with 0, let us say x0 bar covariance, and sigma 0, sorry, x0 bar mean and sigma 0 covariance. And of course, we would have a feedback rule. So this case is called the linear Gaussian case. Linear Gaussian stochastic Markovian system. And in this case, the system is linear, and the noises and initial condition, they are Gaussian. Okay? We're going to talk about this case starting from the next lecture. In general, we have the following important case as well. Nonlinear, additive, Gaussian noise case. And in that case, we can have the following equations. xk is equal to, sorry, xk plus 1 is equal to f of xk uk plus some additive noise, wk here. In general, I can have also G, gain here, really here. It's not important to be that specific. And the noise can again be normal with zero mean and the covariance Q. In this case, the transition distribution would be this. Normal. This is a distribution over xk plus 1. And the mean is going to be f of xk uk. Covariance would be Q. If there is a G here, the covariance would be GQ G transpose. This is nonlinear additive Gaussian case. So you see that the state and the input enters into the state equation non-linearly, but the noise enters, the process noise enters in an additive manner, and the noise is Gaussian. Okay? The output can be similar, and I can have here h of xk plus the measurement noise vk. And vk is with zero mean and covariance r. In that case, the likelihood would be the following. So in the next lecture, we are going to learn about this, and you will have to think about how these can be obtained yourself. So I have here just yk given xk, and this is going to be normal with yk as the argument of the density. The mean is going to be h of xk, and the covariance will be r. If I have a coefficient gain of the noise here, h times vk, the covariance would be hr h transpose. And I would have also the additional input distribution, maybe as a Gaussian distribution. Okay? So sometimes people just use this description, or sometimes they might use this conditional distribution or transition and the likelihood description of the same stochastic system. Okay? And they would be equivalent descriptions. So this would actually finish the chapter of the book called the state space models, and in the next lecture we are going to go into the next chapter called or titled Properties of Linear Stochastic Systems, and we will start working on this type of equations. And actually Kalman filter is going to be an observer for this type of stochastic systems. Okay? So we are going to see the properties of such systems in the next lecture. But that's going to be all for this one. Thank you very much for watching. Bye.